Hello everyone, this is Ajay Garshakurti. Today I am going to explain about my project at Emertxe Technologies titled as EV ADAS Dashboard. So nowadays we are seeing electric vehicles are becoming popular because they are environmentally friendly and energy efficient. However, they require continuous monitoring of important parameters such as vehicle speed, battery charge, and motor temperature, braking and driving range. Along with EV monitoring, modern vehicles also uses advanced driver assistance systems known as ADAS to improve safety by warning drivers. In this project, I developed a STM32. I developed a system that monitors both EV parameters and ADAS features in real time using an STM32 Blue Pill microcontroller and a Python dashboard. The main problem is that raw sensor data is difficult to interpret and traditional serial terminals only display text values without any graphical visualization. Also, basic embedded projects usually lack integrated safety features. To solve this, I developed a centralized dashboard where the STM32 Blue Pill reads sensor values, processes EV parameters, performs ADAS calculations, and transmits the data to a Python dashboard through UART. The dashboard then displays all information graphically in real time. Coming to the objectives, the objective of this project is to design and develop a real-time electric vehicle monitoring system integrated with basic ADAS features. The project combines embedded programming, UART communication, and Python visualization to monitor vehicle performance and improve driver safety. Coming to the tools and technologies, for software development, I used a STM32 Cube IDE for Emertxe firmware development. STM32 Blue Pill. Sorry. I used a microcontroller STM32 F103 CIT6 for the development and Python dashboard for data visualization. Pixim Lab for STM32 hardware simulation. So I used another tools like VSPE and Teratum. VSPE creates virtual connection between common ports between Pixim Lab and the dashboard. Teratum is used to verify UART telemetry during the development. The hardware is built in a Pixim Lab. So the Pixim Lab consists of STM32 Blue Pill, is also known as STM32 F103 CIT6. In the microcontroller, it consists of some features which are analog to digital converter, UART communications, general purpose input output interfaces, potentiometers such as acceleration, brake pedal, state of charge, and motor temperature, and then ultrasonics for collision and detection, and we used LEDs for warning. The programming languages are embedded C. This is used for generating the code for STM32 and Python for visualizing the dashboard. For the dashboard development, we used MATPAT library and MATPAT library for graph analysis, PySerial for UART communication, and custom Python GUI for live electric vehicle dashboard. So the system architecture consists of 4 stages. First one is sensor. The sensor data is processed by STM32 Blue Pill, which calculates electric vehicle parameters and executes ADAS algorithms. The processed data is transmitted using UART communication at 1,15,200 bandpass. Finally, the Python dashboard receives the telemetry and displays all the electric vehicle parameters and ADAS alerts in real time. This slide explains the electric vehicle features. The first one is vehicle speed monitoring. The dashboard continuously monitors the vehicle speed, allowing the driver to know current speed. Second one is the battery state of charge. It displays the remaining battery percentage, helping the driver to understand the available battery capacity. Third one is range. The range predicts how far the vehicle can travel with the remaining battery charge. Next one is brake monitoring. The system also monitors the brake position, which indicates the driver's braking input as a percentage. Next one is motor temperature monitoring. It is continuously monitored to prevent overheating and ensure safe operation. Next important feature is torque. It represents the rotational force produced by the motor. It also displays the torque value in the dashboard. After calculating all the parameters, the STM32 transmits them through UART communication at 1,15,200 bandpass. So this slide explains the ADAS features. The first one feature is front collision detection. It measures the distance to the vehicle ahead. The STM32 compares distance with a safe threshold. If the vehicle comes too close, the system generates a collision warning. The second one is blind spot detection. When two ultrasonic sensors are placed on left and right sides of vehicle, if another vehicle enters the blind spot, the system will immediately update dashboard with warning LEDs and alarms. Third one is time to collision. It estimates how much time remains before vehicle reaches the destination. Time to collision is calculated by distance by vehicle speed. If time to collision is lower, it indicates higher collision risk. The fourth feature is collision warning and alarm. If the time to collision becomes very low, up to the safe limit, the system generates a collision warning and alarm, both visual as alerts. The dashboard and hardware outputs such as LEDs and buzzer are activated. The last feature is fault detection. The STM32 continuously checks sensor operation, UART communication and ADC readings. If any abnormal condition is detected, the dashboard displays a fault indication, making the system more reliable. Now I am going to show the STM32 Cube ID. So this is my overall project. So this is the heart of the project. It is developed based on ARM Cortex M3 processor running at a frequency of 72 MHz. It provides built-in peripherals such as ADC, GPIO, UART, timers, pulse width modulation, SP and I2C. In the EV dash, we have IOC, which means input output configuration. It is used to configure the pin out and clock configuration. We can configure the clocks and we can Here we can configure our pins. So here we can configure our pins based on our requirement. It also consists of system core and timers, for which we should enable. The code consists of two types. One is source code and header code. These two codes are called in the main function. So this is my main program. Wait a minute. So this is my main program. Here we can initialize our program. Also, this is the main file of our project. It consists the total code which we are going to generate. After initializing all the code, we should build our project. If no errors are occurred, we can go with the next step. We should download our binary file. After downloading our binary file, we should go to the Vehcile lab. So this is my Vehcile lab. Here we used a blue pill. The microcontroller is STM32F103CAT6. We have connected it serially to the common 4, which is 1,15,200. So from here, our whole Python dashboard is going to visualize. Based on our inputs, the Python dashboards will going to be changed. So here we are going to map the pins. So this is the potentiometer, which are used for acceleration pedal, brake pedal, state of charge, and motor temperature. And we have 3 sensors, which includes the front, left, and right. This left and right sensor going to indicate the blind spot detection left and right. So LEDs are used for alarms and fault. But the buzzer is used for alarms. The virtual terminal is used for printing the values. So here we can see our values based on the input changes. In the virtual terminal, we are going to transmit and receive the values. So next one is we are going to build the dashboard. For building the dashboard, we are going to use another tool, which is Virtual Serial Port Simulator, also known as VSPE. Here we can configure our common ports. I configure my common ports as common 1 and common 4 and give them a connection. So next one is, here I am going to build the dashboard. For building the dashboard, we should open our command prompt or VS Code. For my specification, I'm going with the command prompt. So after opening the command prompt, we should give our file path. So my file path is this. So we should give as cd space that and our file path. After getting our file path in the menu, we should build the Python dashboard. For Python dashboard, we should give the Python and Python file and the port configuration. After giving the port configuration, we are redirecting to the Python dashboard. So this is my Python dashboard. Now here we can see the speed and the speed history and the battery percentage and left out battery percentage. Here we can see the EV matrices, which includes the torque, acceleration, brake, motor temperature, and alarm, which is in which alarm is advisory or critical or non. Here we can also see the how many faults are being generated. So this is the ADAS bird eye view. From here we can see the if any collision will be occurred or not. So for this, firstly I'm going to the PitSim lab. From these parameters, if we increase the speed, increase the acceleration and decrease the brake, we can see our speed increases rapidly. So mine it is full. So for decreasing the speed, we should increase the brake and decrease the acceleration. So here we can see the values. So the acceleration is 30 and brake is 80. So it will update in the Python dashboard. So here we can see the speed will decrease. Now keeping all this aside, when I increase the acceleration and decrease the brake pedal and decrease the front sensor, I can see the red and yellow LEDs are on, which means collision and fault will be occurred. So here we can see in the dashboard that 4 faults are generated and alarm is critical, and we can see from the bird eye view that collision is going to be happen. To reduce this, now I am going to increase the front sensor. Now the LEDs are off. And the dashboard will update. So the dashboard will update now. I decrease my left sensor. The blue LED will be on. Means the blind spot detection left is occurred. Now the dashboard is updated. When I decrease my right sensor, keeping the left sensor increasing. Now I see the green LED is on, means blind spot detection right is occurred, means the detection is occurring from the right side. Uh, the dashboard is updated. Here we can see the collision is going to happen from the right side. The torque is 0 here. The temperature is 102 and the alarm is advisory and fault is occurred. If I reduce both the left and right sensor, all the LEDs will be on. Means wait a minute. So the dashboard is updated. Here we can see the updated dashboard. In this we can see the blind spot detection left and right going to happen. Before the right side, the collision from the left is going to happen. The alarm is critical and fault is 5. Here we can see the it giving alarms for the driver safety to keep in the safe position. Now when I decrease all the 3 sensors, all the sensor will be on. Now the collision is going to happen from the 3 sides. As we can see, the front here we can see there is a vehicle from the front, left and right. The collision is going to be happen. The collision is going to happen 0 seconds for the front vehicle. So the fault is increased by 1 time and the torque is 0 now. To increase the to decrease the torque in negative, we are waiting for the values from the Pixel Lab. So here we can see the torque is in negative. So this is my overall project. I built a electric vehicle ADAS dashboard in which it gives the speed and battery and speed history and EV metasis and false alarms which are going to be generated and blind spot detections which are going to be happen. It wants the driver to drive the vehicle safely. So coming to the results, the project is successfully completed. In this project, I built a real-time vehicle speed monitoring and which displays the battery and estimates the range, and it also controls the brake monitoring, monitors motor temperature and visualize the torque, and it communicates with the UR telemetry of the band pass of 1,15,200. It also detects the collision and blind spot detection, and I developed a electric vehicle ADAS dashboard by using Python GUI integration. So coming to the advantages, uh, it is a real-time monitoring in which we can see in our daily lives. The dashboard is interactive and we can see if any alarms are generated, so we can interact with it and go to a safe position. The communication is reliable and the sensor integration is easy, so it is very cost effective other than other vehicles. The architecture is scalable and simple. The future scope for the electric vehicles are battery management system. The battery will be managed and GPS tracking can be improved. The connectivity is going to be held between the cloud, and we can use this as a mobile application. And we have a great feature which is AI based driver assistance, in which AI will be assist the driver, and it is a predictive maintenance. So from this project I gained a lots of experience, hands-on experience in embedded C and Python and EV and ADAS features. I thank you to Emertxe Technologies for being supportive throughout the journey, and especially thank you to my mentors. Thank you, everyone.